What? You can't go. Go away. What do you want? You can't have my food. It's not yours. It's mine. Okay. Let's begin today. Every day I get really busy and I forgot to eat lunch, and then it's about like 2:25, and then it's like, oh, I have to go 3 hours without eating now. And so I'm like, oh, and I haven't eaten since this morning. So then I'm like, do I really want to go till 5:30 without eating something? And so I'm always like quickly scrambling for something to eat at 2:30, right before class shows up. So I'm going to be periodically taking a few bites just so that I don't die of starvation along the way here today. Okay. So I quickly made myself a pot pie. One of those little Marie Callender's things. So, right there. My puppy wants it. You can't have it, it's mine. Keeps coming in here. He's a little camera shy. All right. So looks like most people did pretty well on the quiz yesterday. That's good. Okay. This is our last chapter. Okay, we're going to be spending a week and a half in this chapter. It's a long one, and it's pretty involved. So there's 10 concepts that we have to cover in just the first half of the chapter. And then there's the second part of the chapter, and that'll be covered next week or the week after. And then we have a test, and then we have a final. So we got about 2 more weeks of really crunching things. It's Wednesday today, so we're going to go through 4 sections today and tomorrow. Okay. I think it's pretty straightforward, honestly, but some students have really a hard time with this chapter, just like they have a hard time with chapter 7. But I honestly, my personal opinion is chapter 7 is harder than chapter 11, but that's just my personal opinion. Okay, so let's get into the notes today. Real quick here. Move that down. Door. Oh, doesn't like to door. Let's move this down as well. Okay, so today, okay, 11.1 is on sequences. Okay, so example of a sequence. Again, I'm not going to go into all the pre-cal stuff on sequences or all the algebra 2 stuff that you might have been introduced into in high school. I'm just going to go, this is what a sequence is, and this is how we're going to find limits of sequences. So I'm going to focus on the calculus part, hoping that you will have seen this at least once. Now, I know that there is going to be, in a group of 30 people, at least 1 or 2 of you that has probably not seen this, but hopefully you catch on pretty quick. Okay. And if you haven't seen it, you can always come to my office hours on next Tuesday and be like, hey, can you spend some time on sequences? And I'll be like, okay, sure. So, again, hopefully it is pretty self-explanatory. Okay, so let's look at a sequence A sub n equals n over n plus 1. Here's the sequence, right? So n is an index. We call this the index. Okay, and n is an integer, okay, a positive integer. So it starts at 1, okay? N is a positive integer. What we call n is we would say that n is an element of capital N. Does anybody know what capital N stands for? No. Capital N is the natural numbers. So we say n is an element of the natural numbers, and there's always a debate on whether or not 0 is included in the natural numbers. And I don't include 0 in the natural numbers because it makes working with sequences a lot easier. So we're just going to have n start with 1. Okay. So these are the counting numbers or the natural numbers. The whole numbers, I say the whole numbers do include 0, but the natural numbers don't include 0. Okay. Okay. Is everybody following along with me? Is that good? You good? You guys all awake? Okay, if not, go make yourself a pot pie. It'll wake you up. Okay, it'll give you some extra goodness here. Or it could be like my son who sleeps till noon and then needs his caramel mocha frappuccino, and then he's good to go. Like, bro, you slept 12 hours and you still need coffee? He's like, yep. Like, okay. He's like, I need my McCafe. Okay. He can't afford Starbucks. He's poor. He's a poor teenager. So he's got to do the McCafe. Like, I need my iced caramel macchiato frappuccino with whip, something. I don't know. I never understood it. So anyway, so we're going to say A1, A2, A3, A4, okay, all the way to forever. N is you know, a natural number. Okay, this is the first term. Well, it's not a term. It's the first item. I guess we call it a term. I don't know. It's the first. Yeah, we call them terms. Okay, it's the first term in our sequence. This is a sequence. We're going to talk about series in a little bit. Series is when we add these terms together, so they really are terms. But the sequences are terms. They're just separated by parentheses. They're just items set in a list. This would be like listing out values in a set. When we talk about set theory, it's, you know, a set of values. It's a group of values that belong to this certain set. Okay, so what would A sub 1 be? It would be plug in 1, okay, when n is equal to 1, right? So that would be 1 over 2. Okay, what would A sub 2 be? That's when n is equal to 2. So that would be 2 over 3. Okay, what would A sub 3 be? That's when n is equal to 3. And so that would be 3 over 4. Okay, you get it, right? Okay, 4 over 5, blah, blah, blah. Okay, forever. Okay, so that's a sequence. Okay, a sequence of values. Okay, B. Let's look at B here. B is a different sequence. A sub n is equal to -1 to the nth term times n plus 1 all over 3 to the nth term. 3 to the nth power, I should say. Okay, so let's start with n equals 1. Okay, n equals 2. Okay, so plugging in n equals 1, this is -1 to the first power times 1 plus 1 all over 3 to the first power. Okay, let's see what that guy's going to be. This is going to be -1 times 2 over 3. So this is -2/3. Okay, when n is equal to 2, this is -1 to the second power times 2 plus 1 over 3 squared. Okay, so this guy's going to be +1, because that -1 squared is a +1, so that's +1 times 3 is 3 over 9. That's 3/9. Okay, and I could reduce that if I really wanted to 1/3. Okay, but I'll just leave it as 3/9 right now. Okay, what about the next one? This is -1 to the third times 3 plus 1. It looks like the numerator is always going up by 1, and the denominator is always going up by a power of 3. Or how do I say that? By a multiple of 3, sorry. Okay, the power goes up by 1, but the denominator goes up by a multiple of 3. Okay, so what would the next one be? It would be a negative, because -1 to the cubed, okay, and is -4 over 27. And then what would be the next one? This would be +5 over 81, forever, right? Okay, so we see the pattern there emerging. Now, when we get a negative, positive, negative, positive pattern like this, negative, positive, negative, positive pattern, we call this alternating. Alternating. There we go. It's an alternating series, or not a series, sequence in this case. Why? Because it goes negative, positive, negative, positive, negative, positive. Okay, that's what that whole negative 1 to the nth power does. In the original formula for the sequence, this guy here, okay, that guy there alternates. He's the driver between the alternating. Okay, this is what drives that, right? Because the negative 1 to an odd is a negative, but negative 1 to an even is positive. So it just keeps vacillating back and forth, okay, between negative and positive values. If I didn't have that negative 1 to the nth, then this thing would just be all positive. Okay, but this is an alternating sequence. Okay. Okay, C. Let's try this one. A sub n is equal to cosine of n pi over 6. Okay, so this is going to be, you know, A1, A2, A sub 1. I should say A sub 1, not A1. A1 is very tasty steak sauce. Okay, not to be confused with A sub 1, which is not a very tasty steak sauce. So it's making me hungry again. Okay, A sub 1, A2, A3, A sub 4, and so on. No, I cannot say that again. Siri, go away. Okay, so this is going to be cosine of 1 pi over 6, or just pi over 6. This is going to be cosine of 2 pi over 6. Okay, this is cosine of 3 pi over 6. Cosine of 4 pi over 6. Okay, and so forth. Okay, and so what does this become? Well, we could evaluate this on the unit circle, right? These are all pi over 6s on our unit circle. So what's the cosine? Well, that's just radical 3 over 2 of pi over 6. What's the next one? Well, this is just pi over 3, right? So that's 1/2. What's the next one? Well, the next one's pi over 2, which is pi over 2, which is cosine is 0. Okay, and then we just keep going around this thing, every pi over 6. Okay, so this is going to be negative 1/2. This is going to be radical 3 over 2, blah, blah, blah. Okay, forever. Okay, we just continue to go around the circle and forever, ad infinitum. Okay, we would just keep going forever around the circle. And then these would just oscillate. I would get, looks like I would get a cycle of 12. Okay, and then the cycle would just repeat itself after 12 different values in succession, in sequence. Okay. Because every 2 pi I would just do another rotation. Okay. Okay, let's formally define what a sequence is. Okay, did I spell that wrong? Definition. Finite. Definition? I don't know. I can't spell. Okay, definition. A sequence A sub n has the limit L given limit as n goes to infinity of A sub n is equal to L, comma. This sequence has the limit L given, okay, that's how we write it, okay, as n goes to infinity, if, okay, if we can make the terms, can make the terms A sub n as close to L as we like by taking n sufficiently large okay, so we take n sufficiently large to get something that's going closer and closer to a certain value. Okay, then we say that the limit exists. Okay, otherwise, if they're not getting closer and closer to a value, then we say they diverge. Okay, sufficiently large. Okay, if the limit as n goes to infinity, okay, now why is n going to infinity? Because it's a sequence. We're going from 1 to infinity, okay? That's our indices. Our indices are a sub 1, a sub 2, a sub 3, a sub 4, all the way to a sub forever. Okay, if the limit as n goes to infinity of a sub n exists, okay, exists, that is, it equals L, okay, has a limit, okay, exists, we say the sequence converges to L. Okay. Converges to L. So converges, it converges to L. Converges. Okay, okay, if the limit does not exist, a sub n does not exist, comma, we say the sequence diverges. It's divergent. Okay. We could say this also if the limit tends towards infinity. So if it does not exist or it tends towards infinity, then it diverges. Okay. In summary, that is the limit as n goes to infinity of L, or sorry, of a sub n is equal to L if for every epsilon greater than 0 there exists a corresponding integer n, capital N, okay, such that if little n is greater than big N, then the absolute value of a sub n minus L is less than epsilon. Just says, look, okay, say that I have a sequence that starts to converge, okay, to, I don't know, say 1/5. Okay, this thing starts to converge to 1/5. Okay, actually should be a little higher than that. Okay, we'll make 1/5 right here. Okay, so say that this sequence starts to converge closer and closer and closer and closer to, okay, to 1/5. Okay, 1/5 is just an arbitrary value. Okay, then we could say that given any, okay, given at any point, okay, n, okay, there exists a corresponding integer n such that if any n beyond this n, right, then epsilon is the difference between a sub n and the limit, right? So this distance here we're calling epsilon, okay, is the distance between the value and the limit, and we're saying that as little n is, as big N goes to little n, our epsilons get smaller and smaller and smaller and smaller. Okay, so all it's saying is that the gap, it's the gap between, I can get an epsilon that's smaller. The gap is smaller than any of those epsilons. Okay, it just says that the gap here keeps getting smaller and smaller and smaller and smaller. Okay, this is the gap. Think of it as the gap. Okay, not the place that sells really cool, you know, stylish shirts, but the gap between the limit and the term value. Okay, that gap is getting smaller and smaller and smaller. So if you give me an epsilon, say you gave me an epsilon, say, hey, you know what? I want epsilon to be 1/100th. Okay, we're going to say epsilon is equal to 1/100th. Can I find an n, a small n, that's going to beat out the gap? Yeah, I can. I can find out what the corresponding n is. Okay, that would give me an epsilon of 0.01. That gap would be 0.01, and then I can find a newer value for little n, that when I take the gap of that little n, that next value, that's going to give me a smaller value than my imposed epsilon. Okay, that's all that really means. It just says, hey, I'm playing this game where you give me a value and I can find a term that when I subtract it from the limit, it's smaller than the epsilon. Okay, let's try this game. Let's try this game. Let's try this game on something that could work here. Okay, so let's go back to this guy here. This a sub n is equal to n over n plus 1. What do you think the limit of this thing is? What do you think the limit of that thing is? Any ideas? If I just keep doing this, this was like 2/3, 3/4, right? Any guesses on what the limit of this is? 1. Yeah, it's 1. Very good. Okay, not -1. It's just 1. Why? Because we're getting the numerator and denominator are getting closer and closer together, right? So self-serve? Is that like self-serve ice cream? I don't know. I have food on the brain. So self-serve. Oh, like self-serve gasoline. No, I don't get it. Okay, 4/5, right? 4/5. Okay, 5/6, 6/7, right? And you just keep playing this game forever. What if it was 1,000,000? We could do 100 million over 100 million and 1. Oops, that's too many. 100 million and 1, right? So would you say that this is approximately 1? That's really close to 1. That's probably that's probably 0.999999, right? 9, 8, something, blah, blah, blah. Okay, it'll eventually stop because it's a fraction, but it's really, really close to 1, right? So how close do you really want to get to 1? Well, can I get within 1/100th of 1? Well, yeah, I just have to go out far enough if epsilon was my 100th, I could find out, well, what term number, right? What term number n is going to give me something that's, right? So I would say that the limit here is 1, right? So L is equal to 1, right? So I would say n over n plus 1 minus 1. I want the absolute value of that thing to be less than 0.01. So it'd be like, well, how do I get that? Well, I don't know. You could maybe do some algebra. So this is going to be n minus n plus 1 over n plus 1, right? Okay. Is less than 0.01, right? So this is negative 1 over n plus 1 is less than 0.01, something like that, right? Okay, where is this coming from? This is a sub n minus L, right, is less than epsilon. Right, does that make sense? Okay, so we just want an n that's going to beat this thing out. Okay, so what's the absolute value of, well, n is always positive, right? And we never let n be negative, so the bottom's always going to be positive. The negative 1 here, well, dude, that's just the absolute value of negative 1 is positive 1, so I could really just write this as 1 over n plus 1 is less than 0.01, right? Okay, and so I could cross multiply. It says 1 over 0.01 is less than n plus 1, okay? What's 1 over 0.01? Well, that's just 100, which is less than n plus 1, and so 99 is less than n. So we just say that n has to be greater than 99, right? So if n is greater than 99, then epsilon is, less than 0.01. Oh, okay. So we just have to be bigger than 99, or we could let n equal 100, right? We could let n equal 100, and we would beat out this 0.01. Does that make sense? Okay. And if we let n equal 100, we're smaller than this epsilon. Well, what if we let n equal 200? Well, we'd be even smaller. We'd be, okay, instead of 0.01, okay, instead of 0.01, the difference would be even smaller, right? It'd be, okay, it would be, instead of, for this, I would get negative 1 over, well, I'm going to do 1 because that's the absolute value of the difference, right? Again, these things are growing like this, okay? It's growing like this, and it's heading to 1, right? And so we're saying that the distance between these are getting smaller and smaller and smaller. When n is equal to 100, what's that distance? That distance is 1 over 101. Well, what about n is equal to 200? Well, then that distance is 1 over 201. Okay, so it's half as much. Okay, so whereas I don't know what 1 over 1.01 is. It's probably like 0.009 something, right? This is like 0.000999 something. Okay, and then this guy over here, 201, that's going to be 0.000, I don't know, 4999. Okay, so as we go out, it's just saying, look, the difference gets smaller. Okay, and that's some Calc 1 stuff there that, delta epsilon. I'm not going to make you do any delta epsilon proofs in this class. That's for Calc 1 headaches. Okay, we have our own headaches in Calc 2. They don't include taking delta epsilon proofs. But that was the main idea. Where'd my pen go? There it is. Okay. Okay, let's do a theorem. Okay, theorem based on this stuff. Okay, if the limit as x goes to infinity of f sub x equals L, and f sub n is equal to a sub n, when n is an integer, when n is an integer, only integers allowed, integer, okay, then the limit as n goes to infinity of a sub n is equal to L. Okay, so then the limit, okay, pretty self-explanatory. Okay, we're just kind of assigning a function to our formula for a sub n. We're saying, hey, look at this thing. Okay, this is f sub n, but we're only letting n equal an integer, right? Basically a positive integer. Okay, I'm not going to get into the positive or negatives for the integer. It's not necessary. We're always going to basically take these things as starting at 0 or 1. We could let them start as negative integers as well, but that just means we're going backwards in our sequence, and it really just depends on our reference point. Okay, everything's relative, right? According to Einstein. Okay. So when n is an integer, then the limit as n goes to infinity of a sub n is equal to L. Okay. Okay, so again, the idea is if we have a function, say f sub x is equal to 1 over x, then we can make this f sub n is equal to 1 over n, and then we could say, this is a function, but it's only a function of the values where this is an integer. Okay, we don't care about anything else. Okay. We don't care about anything else except for where the dots are on an integer. Boom. Okay, so is this a function? Yeah, it's a function, but the domain is restricted. We're restricting the domain. Why? Because this is going to be a sub n. Okay, that's all we're saying is look at the function, and then we can say, well, for the function, what's the limit? Well, the limit as n goes to infinity of f sub n is equal to 0 in this case, right? Why? Because this is the limit as n goes to infinity of 1 over n, and that goes to 0. So we can say that, oh, if the function goes to 0, then the sequence, the terms of the sequence will go to 0. That's kind of what we're setting up here. So, okay. So another definition, the limit as n goes to infinity of a sub n is equal to infinity means, okay, means that for every positive integer, integer n, m, capital M, there is an integer n such that if n is less than n, then a sub n is greater than m. Okay, again, this is, instead of, think of m as replacing epsilon. Okay, think of m as replacing epsilon. Before we were like, oh, well, the limit goes to some L, and so then the difference between that value and the limit is some small value. It's some epsilon. Okay, some little ones. Okay. And so in this case, we have the opposite effect going on, and that we have things that are continually growing, right? And continually growing, and they're saying, hey, bro, choose an m. Okay, choose an m. Give me an m. Say m is 100, right? Then can I find a value, okay, an integer n, such that when I do a sub n is greater than this n, okay, then a sub n is greater than m. So as we go from left to right, as I increase in my domain, as my domain increases, what do I want to have happen here? Based on this definition, it says, hey, then the range increases. Okay, as the domain increases, the range increases. And if the domain increases, boom, means if I drive my stake at m is equal to 100, then I could say, if n, big N, is bigger than m, right? Or if there's some value n bigger than n, okay, then a sub n is bigger than m. Oh, so m is, let me think about this for a second. No, a sub n, okay, yeah. Okay, a sub n, m is the, I read that wrong. M is the range, m is the range. So this is m here. M is the range, okay, and n, yeah, n is the domain, okay, that makes sense. So n is the domain, right? So say n is equal to 100, okay, the range m, okay, I don't know what that is, I'm just gonna call it m, it's right here, as this thing goes off to infinity. Then what? Then I can say, for some little n that's bigger than m, okay, as I move from left to right, then there's a sub n, which is bigger than, it just says that this thing is growing, okay? As the domain grows, the range grows. That's all it's saying, is that as n is greater than n, a sub n is greater than m. Boom. Just means that it's growing, okay, forever, and therefore the limit is infinity. That's all it's saying. Okay, if this occurs, if the limit as n goes to infinity of a sub n is equal to infinity, okay, then we say the sequence diverges to infinity. Okay, it diverges to positive infinity. It could diverge to negative infinity as well. Okay, but it diverges. If it was negative infinity, we would just have to switch our inequality. Okay. Here, if it's a sub n is less than m, then it's going to negative infinity. Okay, as we move from left to right. Okay, so. Okay, theorem. Another theorem. Okay, if the limit as n goes to infinity of a sub n, absolute value of a sub n is equal to 0, then the limit as n goes to infinity of the original one, a sub n, is equal to 0. Okay. Okay. Nice. Okay, so let's do a quick example of this. Okay, so what does this mean? This means that let's let a sub n equal -1 over n, right? -1 over n. Okay, so this means that, okay, at 1 I would be at -1. At 2 I'd be at -1/2. At 3 I'd be -1/3. Okay, 4 negative. Wait a second. This isn't right. That's not right. That's not right. Okay, if this is true, then at negative, yeah, I have this backwards. Okay, so let's just plug in positive numbers to start off with, because the negatives are going to look like this. The negatives are going to look like that. The positives are going to look like this, right? Okay, because it's a negative there. Flips it upside down. Okay, and we're saying that, look, if this thing, okay, with the absolute value bars, right? If this thing, take the absolute value of that, boom, goes to 0. Well, what's the absolute value of negative 1 over n? Okay, well, it's just 1 over n. It's just 1 over n, right? So we're saying that if this thing, when I take the absolute value of it, goes to 0, well, that's the original. Okay, and the original is going to go to 0. Okay, just saying, look, if taking the absolute value, okay, of the function, it goes, it tends to the same place, okay, as I go off to infinity, well, it's just not going to change. It's not going to change the nature of it. Okay, by flipping it upside down, I'm still going to go to 0. Okay, doesn't change. Okay, so this is negative 1 over n. This is the absolute value of 1 over n. This is just 1 over n. This is the absolute value of negative 1 over n. I'm saying, so if the absolute value goes to 0, then the original function went to 0. Which we know it does. Okay, so this is just an example. Okay, let's do a problem now. Number 1, let's calculate. We calculate the limit at infinity of the natural log. Come on, let's go. Natural log of n over n. That's the natural log of n over n. Okay. Okay. So we're going to treat this as if we were filling in the gaps. Okay. I don't know what this thing looks like right off the hand, but who knows? Okay, so I don't know. Maybe this thing, I don't know. It does some weirdness here and then comes back down. I don't know what it looks like. I guess I could throw it into Desmos real quick and see what it looks like, but it's all good. Okay, so we're just saying, look, okay, when this thing is, okay, well, we know that it's 0 at 1, so that's kind of cool. Okay, that we're going to calculate what this thing is. Now, again, these are just the dots that are for integers, right? But if the dots that are along this function converge, then doesn't the whole function converge? I mean, that's the whole idea behind, you know, our theorem. This theorem here, up here, show you the theorem that I'm talking about. Okay, this one here. Okay, we'll call this theorem number 1. Okay, if the function converges, okay, then this was just an example. Okay, then the individual dots in the sequence would converge. Okay, that's the idea there. Okay, that if the function does. So we're just going to treat this. We're just going to treat this as a function of x. Okay, just let this be x, and then treat this as a function of x. But we're really only interested in these points that are integers. 1, you know, 2, 3, 4. Those integer values. That's the sequence. Okay, but we're gonna fill in the gaps here in order to try to figure out what the limit is. Okay, so x goes to infinity of the natural log of x over x. Okay, so now I want to think about the positive values here, not the whole thing, but I want to think of the positive values. Maybe we'll start at 1 and go up. Maybe we'll say x is you know, greater than or equal to, I don't know, we'll say that x is greater than 0 here, because I don't want to divide by 0, and I don't want to take the natural log of 0. Okay. But now, what can we do to find this? This is going to be infinity over infinity, right? Doesn't this equal infinity over infinity? But now we can use L'Hopital's rule, okay, to find the limit of this thing. So this is the limit as x goes to, I'm going to put an equal sign here. I'm going to go equals with L'Hopital's help. Okay, the derivative of natural log is 1 over x. The derivative of x is 1. So this just becomes the limit as x goes to infinity of 1 over x. Okay, which is 0. We know that that's 0. 1 over infinity goes to 0. So that's 0. Okay, therefore, Okay, what do we know? We know that the sequence a sub n, okay, we'll say that the limit, therefore the limit as n goes to infinity of a sub n, okay, equaling the limit as n goes to infinity of natural log of n over n, natural log of n over n, well, what is that going to be? That's going to go to the same place. It's going to go to 0. Okay, so if the function goes to 0, the sequence also goes to 0. Okay, therefore it's convergent. Okay, it is convergent. Okay, number 2 here. Okay, determine whether the sequence, whether the sequence, okay, a sub n is equal to negative 1 to the nth power is convergent or divergent. Okay. Determine whether this is convergent or divergent. Convergent or divergent. Okay, well let's write out the first few terms of this thing. So this would be negative 1 to the first, negative 1 to the second, negative 1 to the third, negative 1 to the fourth, negative 1 to the fifth. Okay, this is going to be equal to negative 1, 1, negative 1, 1, negative 1. What does it look like it's doing? Okay, well, if we were to start to plot these, right, at 1, this thing is negative 1. So at 1, this thing is at negative 1. Okay, and then at 2, it jumps up to positive 1. And then at 3, it jumps back down. And then at 4, it just keeps oscillating, okay, back and forth between the two. And so it's just gonna jump. It's gonna have these little jumps here. I'm gonna jump from here to here. And then I'm gonna jump from here down to there. And then I'm gonna jump back. And then I'm gonna jump back. And then I'm gonna jump back. And then I'm gonna keep jumping forever and ever and ever and ever and ever forever. Right? So does it converge to a single value? No, it does not converge to a single value. It jumps. It keeps jumping forever and ever and ever. So we say this thing is divergent. Okay. Why? Because it's not convergent. Okay. The antithesis of convergent is divergent. Okay. It's binary. You have to be one or the other. Okay. You're either divergent or you're convergent. And if you're not convergent, you're divergent. Sometimes you diverge, and sometimes you diverge to infinity. But sometimes you're just divergent. Does this thing diverge to infinity? No, it doesn't. But is it divergent? Yes, it is divergent because it doesn't approach a single value. This thing keeps jumping back and forth between two values. It's kind of like schizophrenic, you know. It's like has a multiple personality. It keeps jumping from one to the other, back and forth, back and forth, back and forth. I mean, it's good that it only has 2 personalities, you know, as opposed to 17 or something like that. But you know, it's like Dr. Jekyll and Mr. Hyde here. Keeps going back and forth. Okay, number 3. Okay, let's evaluate. Okay, evaluate the limit as n goes to infinity of negative 1 to the nth power over n if it exists. Okay, does this thing exist? Okay, so here's the deal. Okay, I'm going to use one of our theorems that said that if the limit as n goes to infinity of absolute value base of n equals 0, then the limit, okay, of the absolute value of, or so then the limit of the original goes to 0. Okay, remember that theorem we talked about? Okay, so then this goes to 0. Okay, so let's see if this one goes to 0. The absolute value of it goes to 0, right? So, well, let's think about this for a second. Okay, so let's look at the terms, right? Let's look at the limit as a sub n, or sorry, as n goes to infinity of the absolute value of -1 to the nth term over n. Well, what is that equaling? Right, so the first term would be -1, but I'd have to take the absolute value of that, right? So wouldn't that just be 1? Right, if I looked at the terms, maybe I won't take the limit yet. Maybe I'll just look at the terms. A sub n is equal, well, let's just look at the terms here. So this would be 1, and then it'd be 1/2, and then it'd be 1/3, and then it'd be 1/4, and then it'd be 1/5, right? If I took the absolute values. If I didn't take the absolute values, the original would look like this. It would be negative, positive, negative, positive, negative, okay, forever. So let's look at the difference between these two graphs real quick. This graph goes like that. It's a nice, easy one. Okay, this graph, however, again, oscillates back and forth, okay? But what happens? Well, when at 1, we're at -1. But then at 2, we're at 1/2. Half is high. And then at 3, we're at -1/3. And then at 4, we're at 1/4. And then at 5, we're at -1/5. So what is it? Even though it's oscillating, what is it doing? It's oscillating a lot slower, and it will eventually approach what? What do you think this one eventually approaches? Okay, well, that one's going to eventually peter out and approach 0. Right? Does that make sense? It's getting closer, even though it's jumping back and forth, it's getting closer and closer and closer to 0. Now we can prove that using that theorem that says, if the absolute value, which is this one, well, does that one go to 0? Yeah, absolutely. We know that one goes to 0. Okay, that one goes to 0. We're good with that. Okay, and so we can say, since the limit as n goes to infinity of -1 to the nth power over n, okay, equals the limit as n goes to infinity of 1 over n is equal to 0. Okay, so since that limit goes to 0, okay, since, okay, no comma, since the limit of this guy is equal to 0, then the limit of the original guy, okay, is also 0. The nth power over n is also equal to 0. Okay, so what this tells me is that if a sequence, okay, tends towards 0, then its alternating counterpart also tends towards 0. Okay, also tends towards 0. Okay, let's look at another theorem here. Okay, it doesn't matter that it alternates, it just, the terms are decreasing. So they're getting closer and closer to 0. Okay, another theorem. If the limit as n goes to infinity of a sub n is equal to L, if the limit equals L and the function f is continuous at L, then the limit as n goes to infinity of f of a sub n is equal to f of L. Okay, so that's kind of cool. So if we nestle this sequence inside a function, then the limit would be nestled inside that function as well. Okay. So let's see what happens here. Number 4. Find the limit as n goes to infinity of the sine of pi over n. Okay. So what we can do here is we can use this kind of function here and say, well, what's the limit of just a sub n? What's the limit of a sub n? Well, we're going to say, what's the sine of the limit as n goes to infinity of pi over n? Right? Okay, because we're going to say that those two are equal based on this previous theorem. That if the limit of a function goes to something, then the function of the limit will go to the same place. Okay. And so, well, what's the limit as n goes to infinity? Well, pi is just a number. Pi divided by infinity is 0. This thing goes to 0. And so what's the sine of 0? Well, it's just 0. So this original one went to 0. That was easy.
That was easy.
Yes, it was. Okay. Okay, the sequence. Okay, r to the nth power. That's an r, by the way. Let's make it look more r-ish. There we go. R to the nth power is convergent if and only if, okay, r is a fraction. Okay. Okay, or 1. If it's 1, it just converges to 1. Okay, but if it's a fraction, it's also convergent. Okay. Okay, so right, so if this thing, if r is a fraction, now why is this? Let's take a value in between here and let's just play with it. Let's look at 1/2. R equals 1/2. Okay, so we're saying that the sequence here, 1/2 to the nth power, that sequence a sub n, the limit of that as n goes to infinity is it converges, right? It has a value, it has a limit. Okay, that doesn't tell me what the limit is, but it just tells me, hey, it's convergent. Okay, so well, let's see what happens here. If the limit as n goes to infinity of 1 over 2 to the nth power, that would be the same thing as the limit, okay, as n goes to infinity of 1 over 2 to the nth power, right? Because 1 to the nth is just 1, so I can just kind of drop that. Okay, and so this is 1 over 2 to the nth. Well, what's going to happen to this 2 to the nth? Isn't that going to go to infinity? So wouldn't this whole thing just go to 0? Yeah. So we can kind of summarize that if this is a fraction, the limit goes to 0. Okay. If r is 1, however, what's the limit as n goes to infinity of 1 to the nth power? Well, that's just 1, right? Because 1 to anything is itself. Right, this would be 1 to the second power, 1 to the third power, 1 to the fourth power. It's just 1. So there's 2 scenarios here for the limit as n goes to infinity of r to the nth power. There's 2 scenarios. So I'll set up a a piecewise scenario here. Okay, if it's 0 if it's a fraction. If r is a fraction, it's 0. Okay, it's 0 if it goes from -1, okay, to r to 1, it's 0. And it's 1 if r equals 1. Okay. Okay. Keep going. Keep on trucking. Okay, definition. A sequence is called increasing if the sequence is called increasing if a sub n is less than a sub n plus 1, okay, for all n greater than or equal to 1. It is called decreasing. Okay, so this means that it's going up. Okay, increasing if a sub n is less than a sub n plus 1. Okay, it's decreasing if a sub n is greater than a sub n plus 1 for all n. Okay, greater than or equal to 1. So decreasing if a sub n is bigger than a sub n plus 1. Okay, so it's decreasing. Okay, let's see if something is decreasing or not. Is a sub n equal n over n plus 1 decreasing? Is that decreasing? Oh, not n plus 1. N squared, I should say. N squared. Is that decreasing? Okay, the other one, okay, would not be decreasing. But is this one decreasing? Is this one big enough to be decreasing? Okay, does it continue to go down? Okay, so we want to prove this is decreasing. Well, how would we prove that this is decreasing? Well, we need to know that a sub n is greater than a sub n plus 1. I'm going to put a little question mark here. Is a sub n greater than a sub n plus 1 for all n? Okay, is this true? Question mark. Is a sub n greater than a sub n plus 1 for all n? Okay, well, what is a sub n? A sub n is n over n squared plus 1. What's a sub n plus 1? What's the next term? Well, wouldn't that be n plus 1 over n plus 1 squared plus 1? I think so. Okay, and I want to say, again, is this true? Is this greater? Is this always going to be the case? Does this have to be the case? Or is there a counterexample here? You only need one counterexample to prove something false. Okay, but you need no counterexample to exist to prove something true. It's much easier to prove something's wrong than to prove something's right. Okay, we're gonna attempt to try to prove, is this decreasing? Does it work all the time? Okay. Think about this for a second. Well, what am I going to do here? I'm going to cross multiply. Okay, I'm going to cross multiply. And see if the inequality still holds. So I'm going to go n plus 1 squared plus 1 times n. Is that greater than n squared plus 1 times n plus 1? Okay. Cool. Okay, So let's multiply this out. This is going to be n squared plus 2n plus 1 plus 1 times n is greater than, this is n cubed plus n squared plus n plus 1. Multiply this out. This is n cubed plus 2n squared plus 2n is greater than n cubed plus n squared plus n plus 1. Okay, let's subtract. Let's subtract n cubed, n squared, and n. N cubed, n squared, and n. That goes away. And so this says that goes away. It says that n squared plus n is greater than 1. N squared plus n is greater than 1. Okay. Is that true for n greater than or equal to 1? Is that true? If these numbers are positive, is there ever a case, is there ever an n that's going to get me a number smaller than 1? Because if my smallest value here is 1, right? If my smallest value here is 1, that's 1 squared plus 1 is greater than 1. Well, that's 2 is greater than 1. I'm already at 2 just by starting at 1. And since I have no negative numbers here, this is always going to be true. This is always true. Always true. So since the inequality holds, since n squared plus n is greater than 1 for all n greater than or equal to 1, then what do we know? Then we know that a sub n is greater than a sub n plus 1. It means that we're going downhill. Therefore, what do we know? We know that a sub n is equal to n over n squared plus 1 is decreasing. Okay, it is decreasing. Okay. Little happy face. Yay. Okay. Okay, a sequence is said to be monotonic if it is always increasing or always decreasing. It's either always increasing or always decreasing. Then we have the special word called monotonic. Okay, it's one direction. Okay, not to be confused with this very awful boy band from the early 2000s. Okay, so it's one direction. It always goes one direction. Okay. 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 Since a sub n equals n over n squared plus 1 is always decreasing, it is monotonic. It can be proved to be monotonic. It's always decreasing. Okay. Okay. Definition. Whoa, what the heck happened there? Definition. Okay, a sequence a sub n is bounded above if there is a number m, capital M, such that a sub n is greater than, or sorry, a sub n is less than or equal to m. Okay, for all n greater than or equal to 1. Just says that, hey, you know what, if I'm going out here, okay, and here's m, okay, and a sub n is always less than n, then there's a boundary, okay, it's bounded above by m. Okay, okay. Conversely, if a sub n is greater than or equal to m, for all n greater than or equal to 1, it is bounded below. Okay, it's bounded below. Okay, so once again, okay, say that it's bounded below by some m. Okay, boom. Okay, it just says that a sub n is always bigger than m. Okay, it just says there's some sort of boundary below. Okay, and a theorem that comes out of this definition is that every bounded monotonic sequence, so every bounded increasing or decreasing, okay, that's what monotonic means. Every bounded monotonic sequence is convergent. Okay, it's convergent. Okay, and that's sequences, people. Sequences. That's all I got to say on sequences. Okay, let's camp. Okay, the only real big thing that I want you to get out of that, the big idea, okay, is that, you know, these sequences converge or they diverge. Okay, the sequences do. Okay, because now we're going to start talking about series, what happens to series, and that's when we start adding these things together. Okay, what's the deal with the series here? Okay, that these things will converge or diverge, right? We saw that the sequence 1 over n converges. We saw that the sequence, I don't know, what else? We saw the sequence -1 to the nth power. Okay, that diverged. That didn't diverge to infinity though. Okay, diverged to something else. What was one that diverged to infinity? I don't know. Did we do one that diverged to infinity? It doesn't matter. We'll just do a sub n is equal to n squared. That one's going to diverge to infinity. It's going to go up forever. Okay, so divergent. Okay, a sub n is equal to 1 over n. Or sorry, convergent. I got this backwards. Convergent. And then we've got divergent here. Okay, let's go into 11.2. And we're going to talk about series. We're going to talk about 10 different ways over the next week, 10 different ways that we can prove a series convergent. Okay, or divergent. Because if it's divergent, it's not convergent. Okay. So 10 different ways we could prove a series converges. Okay. We're going to cover 2 of those today. Okay, 2 of the 10 today. Okay. Okay, so let's go back into a brief understanding of what a series is. A brief review, I should say, of what a series is. A1 plus A2 Okay, we call this S sub n. This is, okay, or S, we could call this S. Sum, the sum of this thing. Okay, if we want to make it an infinite series, let's call that S. Okay, the series, okay, if it stops, it's S sub n. Okay, but if it goes on forever, it's called S. Okay, S equals a sub 1 plus a sub 2 plus a sub 3 plus dot 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 is called an infinite series and is expressed using summation notation. I like saying that, summation notation. Just because it rhymes. It rhymes nicely. Summation notation on a Dalmatian plantation. Forget it. Okay. So n equals 1 to infinity of a sub n. Okay, so we use summation notation there to express, okay, our sum. Okay. Okay, so for example, okay, we have n is equal to 1 to infinity of 1 over 2 to the nth power. This is going to be 1/2 plus 1/4 plus 1/8 plus 1/16 plus dot 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 forever. We're adding increasingly smaller and smaller terms. Okay, this thing will eventually converge to a certain sum. It's not that it's converging to 0. The terms are converging to 0. The sequence converges to 0, but the sum will converge to a number. Okay, a value here. Okay. So we talk about the partial sums. We talk about the whole sum, the sum of the whole thing. We also talk about the partial sums, okay, or S sub 1. Okay, that's just the sum of the first term, which is just itself. Okay. S2 is the sum of the first two terms. So this is going to be, what, 3/4? Okay. Okay, S sub 3 is equal to, okay, it's equal to the first three terms. That's 1/2 plus 1/4 plus 1/8. What's that going to equal? That's 4/8 plus 2/8 plus 1/8. That's 7/8. Anybody want to have a wild guess as to what this thing sums to? And at the very end? S sub n is equal to, okay, this is going to be 1, 3. This is going to be n, or 2 to the nth minus 1 over 2 to the nth, right? Is that, and not always 2 to the nth minus 1 over 2 to the n. So eventually, as this thing goes to infinity, this is going to get closer and closer to 1, right? Okay. So yeah, exactly. Right? Because they're only a difference of 1 away, always. And that difference becomes very negligible. Okay. So S, what we do is we say S sub infinity. Okay, S sub infinity is equal to 1. Okay, we could say S sub infinity or just S, just the S. S, I'll just go like this. S sub infinity, which is equal to S, is 1. This thing sums up to 1. Okay, so it's kind of interesting. Partial sums, right? Partial sums. Again, what did the limit of 1 over 2 to the nth go to? Wasn't that 0? Doesn't the original sequence go to 0? Don't the terms go to 0? But what did the sum go to? The sum went to 1. So when I added up these terms, they kept going to 0. It means we were just adding up smaller and smaller values. Okay, these values here, 1/2 and 1/4 and 1/8 and 1/16, right? And we just kept adding smaller and smaller values. So the entire sum, when I add these up, dot, 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 forever, okay, the sum as we go off to infinity is 1. Okay, that's kind of cool. Okay, let's do a definition and let's explain why this thing is summing up to 1. Okay, why is it converging to 1? Why is the series converging to 1? Okay, the series converges to 1 when the sequence converges to 0. We're going to see that if the sequence does not converge to 0, it will never converge. If the sequence does not converge to 0, if the terms are not getting smaller, the series will never converge to anything. Why? Because think of it backwards here. Think about if I kept adding bigger and bigger numbers. Right? If I kept adding bigger and bigger numbers, wouldn't I just keep getting bigger and bigger sums? Does that make sense? So you have to keep adding smaller and smaller numbers, otherwise it doesn't sum to anything. It just it goes off to infinity. Right? So if I kept adding, like this was a 3 and then a 4 and then a 5 and then a 6 and then a 7, right? I keep adding bigger and bigger numbers. What's happening to the sum? The sum just keeps getting bigger and bigger. Okay, so that's the idea. Okay, let's look at a definition. Okay, given a series, no, not theory, a series. I got to turn my damn phone off. Okay. What? It's technology today. Shut up, Siri. I'm not talking about you. Okay, given a series, okay, n equals 1 to infinity, a sub n, I'm going to tell my family that. That's pretty funny. A sub 1 plus a sub 2 plus a sub 3 plus a sub 4. Okay, plus dot, 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 dot. Okay, let S sub n denote the nth partial sum. Okay, the nth partial sum. So S sub n is equal to a sub 1 plus a sub 2 plus a sub 3 plus a sub 4 plus dot, 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 plus a sub n. Okay, which equals the summation of n equals 1 to I. Actually, let's reverse that. I equals 1 to n. I equals 1 to n of a sub n. Oh, a sub I. Yeah, a sub I, there we go. Yeah, okay, and okay, S sub 1, comma, S sub 2, comma, S sub 3, comma, S sub 4, comma, all the way to S sub n is the sequence. Now this is the sequence of partial sums. Okay, think of this as like before when we had our partial sums, we said, oh, well, this is 1/2, and then 2/3, and then 3/4, and then 5/6, and blah, 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 right? Well, it wasn't that. It was, sorry, it was 1/2, and then it was 7/8, and then it was 15/16, and then it would be 31/32, and so on and so forth, right? That would be the sequence of partial sums. Okay, dot, 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 to S sub n. Okay. Okay, is the sequence. Okay, this is just an example. Okay, sequence S sub n. If this sequence is convergent, which we saw that it was here, if the sequence S sub n is convergent. Okay, and the limit as n goes to infinity of S of n equals S. Okay, so we're saying let S be the sequence of partial sums that go off to infinity. Okay, and okay is a real number. So the limit exists, and it's a real number. Then the series summation a sub n is what we call convergent. Okay, so if these partial sums get closer and closer to a certain value, then the original series is convergent. And its sum is S. Okay, that is the summation of a sub n's is equal to S. Otherwise, if not true, then a sub n is divergent. Okay, it either converges to a number or it doesn't. Okay, it's divergent. Okay, let's look at our first test for divergence. We're going to have 10 tests. 10 tests. 10 tests for convergence or divergence. Okay, 10 of them. Let's look at test number 1. Test number 1. Test number 1 is called the geometric series test. Okay, the geometric series test. And what does the geometric series look like? Well, it's the summation of x to the nth power as n equals 1 to infinity. Okay, what does this look like? Well, looks like 1 plus x squared. Sorry. What do I want to do here? X to the nth, x squared, x, yeah. Let's start at 0, actually. No, let's start at 1, and we'll just change our index to n minus 1. There we go. That's better. Okay, so this is the geometric series. It's called a power series as well, but we'll get into that more later. X to the n minus 1. Okay, so what does it look like? This looks like x to the 0 plus x to the first plus x squared plus x cubed plus dot 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 dot. Right? Okay, this is called a geometric series. Okay, it looks like this. And we could have a constant in front of that if I really wanted to. I could have some sort of constant. I'll rewrite this in a minute. But what does this equal? This equals 1 plus x squared plus x cubed plus dot 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 dot. And this thing is convergent. This thing converges if and only if, okay, x is a fraction. X is a fraction. Oops, what the heck? Come back. Okay, it converges if and only if x is a fraction. If x goes from, okay, -1, okay, to 1, okay, to 1, this converges, okay. If it equals 1, then it just converges to 1. Well, no, it doesn't converge to 1. It diverges. So if it is 1, it diverges. If it's -1, it also diverges. But if it is anything in between -1 and 1, it converges. Okay, why would it diverge if it was 1? Well, if it was 1, I'd just keep adding 1s forever. But if x is a fraction, if it's a fractional amount, then it converges. Okay, And so we call this thing, we label this x value, we label him r, and this is called the radius of convergence. Radius. Well, we won't talk about that. Okay, this is just the r. Well, yeah, we'll talk about that. It's called the radius of convergence. Radius of convergence. Let me rewrite that. Radius of convergence. Okay, radius of convergence. That's r. And I'm going to rewrite this thing, okay, as s is equal to the summation of n equals 1 a, sub a is just a constant. You can have a constant in front. Okay, r to the n minus 1 to infinity. Okay. Okay, this is equal to a plus ar plus, okay, ar squared plus ar cubed plus dot, 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 okay, all the way to infinity. The partial sum of this thing, a sub n, or sorry, s sub n, is equal to, okay, okay, is equal to the sum as n equals 1, no, I want to do I this time, as I equals 1 to n. This is the nth partial sum of a to the r to the I minus 1. Okay, and there is a formula for this. Okay, and that is a times 1 minus r to the nth all over 1 minus r. Okay, that will give me the sum of the first n terms. Okay, this will be the sum of the first n terms. Let's see how this works. Okay, let's see how this works. Let's look at our example before when we had r is equal to 1/2, a is equal to 1. Okay, so we had this before. You maybe didn't know that it was a geometric series, but what happens when we do the summation as n equals 1 to infinity of 1/2 to the nth power, right? What was that? Well, that was just our 1/2 plus 1/4 plus 1/8 plus 1/16 plus 1/32 plus 1/64 plus dot, 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 forever, right? And this is saying that S sub n is equal to a, okay, in this case, a is 1, because there is no number in front, so this is just a 1, a times 1 minus r to the nth power all over 1 minus r, 1 minus r. Okay, so let's say that let's do s sub 3. Let's make it easy. S sub 3 would be the sum of the first 3 terms, right? That would be the sum of the first 3 terms, S sub 3. So the sum of the first 3 terms, well, what's a? A is 1. This is 1 minus 1/2 to the third power all over 1 minus 1/2. Oh, okay. Okay, let's see what we get here. So, yeah, 1 minus 1/2 to the third, that's 1 minus 1/8. Okay, cool. Okay, and then this is 1 minus 1/2, that's 1/2, right? 1/2, okay. So what's this going to be? This is going to be plus, okay, let's see what we get here. So this is 7, 8/8 minus 1/8 is 7/8 over 1/2. Okay. So let's see what we get. So then, did I do this right? Looks like I'm doing this right. Yeah, let's just keep going. Okay, so this is going to be 7 over 8 times 2 over 1. This looks like it's 7/4. 7/4. Let's see if this works out. Okay, let's add up the first few terms here. 1/2 plus 1/4 plus 1/8. Let's see what happens. 1/2 is 4/8. I know that. Okay, plus this guy is, okay, 2/8 plus 1/8. That doesn't make sense. Okay, why am I not getting 7/8? 1 minus 1/2. Oh, I know why. I know why. I know why. I know what I did wrong. Okay, A is not 1. A is not 1. I don't think. No, A is 1. A is, A, A is 1. A is 1. Why is this not working out? Okay. There I'm getting 7/8. There I'm getting 7/4. Let me think about this for a second. Oh, wait. Because it's not to the nth power, it's the n minus 1 power. Ah, that's what it is. Okay. So this is 1 plus this. Okay, there we go. Now that makes more sense. Ah, okay. Okay, let me. So it's A to the 1/2. Let me redo this here real quick. Okay. That's why we invented erasers. Okay, let's see. Let's see what we got here. Okay, 1/2. Oh, right. So it's this thing that's the first 3 terms. Aha, okay. So this is n minus 1. Yeah, it's got to be n minus 1. So this is the first 3 terms. So I was adding it wrong. Okay, so this is S sub 3. Stop. Go back. What did I do wrong? There we go. Okay. Hello. Hello. There we go. Okay. So this is S sub 3. S sub 3. So now when I do this, S sub 3, okay, it's 1 plus 1/2 plus 1/4, which is equal to 4/4 plus 2/4 plus 1/4, which is 7/4. So it does work out. It does check out. Okay. Yeah, I just have to make sure that that's to the n minus 1 power. Okay. Okay. What if I wanted it to start at 1/2 though? What if I wanted it to start at 1/2? What could I do here if I wanted to start at 1/2? So what if I just wanted it to be 1/2 plus 1/4 plus, or 1/8 plus dot dot dot? Well, I'd have to make 1/2 my A. I'd have to make 1/2 my first term, my A, the thing that I'm multiplying by. Because then what happens is, right, is think of it this way. Okay, think of it this way. Let's think of it a different way. It'll make more sense, I think. Okay, so if I take my original one here, right? So 1 plus 1/2 plus 1/4 plus 1/8. 1/8, come on. Okay, plus dot 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 dot, right? And what happens if I multiply the whole thing by 1/2? What happens then? Well, doesn't that just become 1/2 plus 1/4 plus 1/8 plus 1/16, right? Doesn't that just multiply the, so what is this? This is my A, right? A in my formula, A R to the I minus 1, okay, as I equals 1 to n, right? So this is for my nth partial sum, S sub n. Well, what would a be? A would be that value there, 1/2. So this would be 1/2 times 1/2 to the n minus 1, right? And so they're saying that in this case, it's a, the sum of this thing is a to the 1 minus r to the nth term all over 1 minus r. Okay, so what's a? A in this case is 1/2. It's the 1/2 that I had to multiply by. Okay, and then if I wanted to get the first three terms of this thing, then of s sub 3, right? So let's move this down. Okay, I really want to get that 7/8. That's what I'm looking at getting, that 7/8 there. It's bothered me that I didn't get it before. I'm going to manipulate it so that I can. So this thing is going to be equal to 1/2 times 1 minus 1/2. It's still 3 terms, so to the third power, all over 1 minus 1/2. Okay, so what is this going to be? This is 1/2 on top, and this is 1/2 on bottom. What's going to happen to the 1/2s? They're going to cancel. This just becomes 1 over 1 over 2 to the third power, which is 1 minus 1 over 8, which is 7/8. There you go. Okay, so yeah. Anyway, that was kind of a little trail off the beaten path, but it was a good mental exercise. Okay, if, what do we leave off here? Okay, so it converges. The sum of this is this thing. Okay, S, if we want to talk about S, okay, the entire sum, then this is what we call a sub 1. It's the first term, okay, a sub 1, or just a, okay, just a, okay. Why is a sub 1 always a? Well, it's just because of the way this function is. What happens when I plug a 1 in here? What's 1 minus 1? It's 0. What's r to the 0th power? It's just 1. What's 1 times a? It's a. So you can think of this as a sub 1, or you can think of it as a. It really doesn't matter either way. It's a over 1 minus r. Okay, so that's the sum. That's the infinite sum. If you want to put an infinite symbol there, you can. An infinity symbol, you can. Okay, but just know that that's the same as this thing. Okay, so the total sum, total infinite sum, is this thing. Now, why is it this thing? Well, what happens when we take the limit as n goes to infinity of a to the 1 minus r to the nth all over 1 minus r? Oh, okay. Well, keep in mind that you know that r is a fraction, right? R is a fraction. Okay. So if r is a fraction, if r is a fraction, then what does r to the nth power go to? If r is a fraction, think of it as like 1/2 or 1/4, right? What is 1/2 to the nth, or 1 over 2 to the nth? What will that always go toward? Well, that will always go towards 0, right? Okay, so this thing will always go towards 0. What's 1 minus 0? Well, that's just 1. What's 1 times a? That's a over 1 minus r. So this thing is equal to a over 1 minus r, which is exactly what the sum, infinite sum, goes to. Okay, that's kind of cool. Okay, so that's geometric. Okay, so let's take an example here. Number 1 is the series. Okay, the summation as n equals 1 to infinity of 2 to the nth power, or sorry, 2 to the 2nth power times 3 to the 1 minus n, convergent or divergent? Convergent or divergent? Okay, does it decrease or does it increase? Okay. Okay, so what I want to do is some manipulation here, so I only get one n. Okay, I'd like to get just one n there. Okay, and so I'm going to rewrite this 2 to the 2n as 2 squared to the nth. And I'm going to write this 3 to the 1 minus n as 3 to the first times 3 to the negative n. Okay. And so this becomes 3. I'm going to pull that 3 of the first out in front. This becomes 3 times 4 to the nth over, okay, over 3 to the nth. Okay, cool. So we want the summation of n equals 1 to infinity. Okay, and so this is a 3 times 4 over 3 to the nth, n equals 1 to infinity. Okay, so, okay. And so this has a common ratio. Okay, this has a common ratio. I could rewrite, I could even further rewrite this as this if I really wanted to. Okay, I could go n equals 1 times or to infinity. Okay, of 3 times 4 thirds. I'm going to break off of 4 thirds here. 3 times 4 thirds times 4 thirds to the n minus 1. Now it's getting closer to that geometric series form. Okay, the 3's are going to cancel, so I'm left with 4. Okay, so 4, this is the summation n equals 1 to infinity of 4 times 4 over 3 to the n minus 1. Now, what is my common ratio? My common ratio, r, is 4 thirds, but that's bigger than 1. And what happens when the common ratio is bigger than 1? This thing just keeps growing without bound. And so since r is greater than 1, the series will diverge. Okay, the series diverges by the geometric series test. Okay, by the geometric series test, it diverges. Okay, it's not going to converge because it's not a fraction smaller than 1. Okay, it's got to be less than 1. Okay. We call this r it's actually called the common ratio. I called it the radius of convergence before. It's not. This is the common ratio. Okay, r. Okay, number 2. Find the sum of the series. Find the sum. Right. Find the sum x to the nth as n equals 0 to infinity. Notice it's starting at 0 this time. Okay. Find the sum. Sum is equal to this. Okay. So find the sum, okay, of this series. Okay, when the absolute value of x is less than 1. Oh, okay. So what? So let's try to start this at 1. Okay, so I can think about this. Well, this would be, let me think about this for a second. So what is this going to look like? Well, this thing, if I did x to the 0 plus x to the first plus x to the second plus x to the third, right, starting at 0, this thing looks like this. And this is 1 plus x squared plus x to the third. That looks like a geometric series. Okay, where what? Where if I just change the n to n minus 1, I can change the index, right? So if I go up 1 for the index, then I can go down 1 for the power. If I go up 1 for the index, and that should be the exact same thing I got before. Because again, I want to compare this to the geometric series where a is equal to 1 and r is equal to x, right? But what are we saying? We're saying that x is less than or equal to 1. So therefore, this thing does converge. This converges, okay, since the absolute value of x is less than 1. Therefore, what's the sum? The sum would be a over 1 minus r. But what is a in this case? It's 1. What is r? It's x, and so it converges to 1 over 1 minus x. Whatever x was, okay, whatever that common ratio is, okay, then it will converge to 1 over 1 minus that. Okay, number 3 here. Okay, find the sum okay, of the series n equals 1 to infinity of 1 over, oops, move down, 1 over n times n plus 1. That's an interesting one. 1 over n times n plus 1. Okay. So what I'd like to do is I'd like to break this up into 2 separate summations, okay, using some properties of sums. Okay. So what I'm going to do is I'm going to use partial fractions. To break this up. So I have 1 over n times n plus 1 is equal to a over n plus b over n plus 1. Cool. I like what I've done there. Yes, very pleased. Okay, so now what I'm going to do? Well, I'm just going to multiply through by the common denominator. 1 is equal to a times n plus 1 plus b times n. Oh, okay. Nice. Again, I like what I've done there. Okay, let's distribute the a. 1 equals a sub n, or a n, not a sub n, a times n plus a plus b times n. Okay, b times n. Okay, I'm going to collect the like terms. I'm going to go a plus b times n, okay, plus a is equal to 1 plus 0 n. So what do I know? I know that a had to be equal to 1, because that's the only constant term. A equals 1. I also know that a plus b has to be equal to 0. Okay, so then a is equal to negative b, and so b had to be negative 1. Oh, okay. So we're going to say the summation of 1 over n times n plus 1 is equal to the summation of 1 over n, a over n, plus negative 1 over n plus 1. I'm going to make the negative go with the with the sign, okay, with the subtraction sign. So it's negative 1 over n minus 1 over n plus 1. Oh, okay. Okay, so that's what we've got. And we're going to go from n equals 1 to infinity. We'll see what I can do with this thing. Okay, find the sum. What does the sum of this thing equal? Okay. What does s equal? Okay, so let's start plugging in some terms here and see what happens. Okay. So, see what happens. So, I'm going to get 1 over 1, which is 1, minus 1 over 2, plus 1 over 2 minus 1 over 3, plus 1 over 3 minus 1 over 4, plus, you see a pattern arising here? Okay, times 1 over plus 1 over 4, plus, okay, plus 1 over 4, minus 1 over 5. Okay, plus dot, 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 dot. And what is this? This is the limit as n goes to infinity of 1 over n minus 1 over n plus 1, right? Okay. Okay, so we want to know what's the limit of this thing as it goes to infinity, right? What's that going to go to? Okay, nice, nice, nice. Well, this thing, what's 1 over n? Well, that thing goes to 0, doesn't it? That thing goes to 0. 1 over infinity. Well, what's 1 over infinity plus 1? Well, that's still 0. So this whole thing goes to 0. Okay, so it just says that you're going to get smaller and smaller and smaller and smaller. You're going to get so small that they eventually go to 0. Okay. What happens to all the other terms here? What happens to all the other terms? We've got 1 minus 1 half plus 1 half minus 1 fourth plus 1 fourth minus 1 fifth. We would have a plus 1 fifth. And we just keep going forever, right? Adding and subtracting as we go. Minus 1 sixth plus 1 sixth, dot, 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 right? And eventually these things are going to get so small that they go to 0. And so what happens is I get to cancel out everything except for the first term. What this is called the telescoping or telescoping. The telescoping series. Why is it telescope? Because it kind of folds in on itself. Okay, think of those old-timey telescopes, right? Like what the pirates used to have, right? And they used to be like, oh, right? And so they fold up on itself, right? And so it telescopes. So you end up with the front and you end up with the back, and everything in between kind of goes away. Okay, it telescopes in on itself. So this is called a telescoping series. Okay, telescoping series. And so what's the only thing that survives is that 1. So the sum is 1. Again, it's called the telescoping series. Maybe it's my lunch. Stop it. Behave. Oh, behave. Okay. Number 4. Number 4, show that the series that, I can't even spell more. Come on, erase, dang it. I think it's not erasing because my screen is so gosh dang dirty. Erase. Erase it. There we go. Oh, look at that. It's all gone. No, it's just here. Okay. Come back. There we go. Okay, show that. Come on. Be nice to me. Okay, show that the series, oh, it is writing much nicer now. The series summation n equals 1 to infinity of 1 over n diverges. Okay, this series has a special name. Okay, the series 1 over n as n equals 1 to infinity. This is 1 plus 1 half plus 1 third plus 1 fourth plus 1 fifth plus, you get the idea. This is called the harmonic series. Okay, it's the harmonic series. We want to prove that this thing is divergent. Okay, we want to prove or show that this thing is divergent. And this is a arithmetic proof that this thing is divergent. We want an arithmetic proof of this. Okay, this is an arithmetic proof. Proof or algebraic proof. Okay, really is more of an arithmetic proof because we don't use algebra, we use just numbers in this thing. Okay, so let's look at the sums, right? We want to know if it's convergent, it's going to sum to something, right? So if convergent, okay, Okay, if convergent, then this thing is going to sum to something. Okay, something nice. Okay. S is going to equal some sort of a real value. Okay, then the sum, the infinite sum is equal to a real value. That's if it's convergent, right? Okay, so if it's divergent, then it doesn't. Okay, so notice that the terms are going down, right? That they're going down. So just because the terms go down doesn't mean that it's necessarily a proof of convergence or divergence. If they go up, it's divergent automatically. But notice that the limit as n goes to infinity of 1 over n is equal to 0. So the limit, these values converge, but we're going to see soon that it's not going down fast enough, that they're not going down fast enough for it to not diverge. Okay, it's not convergent. Okay. Okay, so let's do our little proof here. Okay, what's S sub 1? S sub 1 on this thing, okay, is 1. What's S sub 2, right? So what is this 1? 1 plus 1/2 plus 1/3 plus 1/4 plus such and such. Okay, what's S sub 2? S sub 2 is 1 plus 1/2, which is 3 halves. Okay. 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 Okay, on the next one, okay, S sub 3, this is 1 plus 1/2 plus 1/4. Okay. Okay, we'll just table that for right now. Okay, I'm not gonna focus too much on that. What's the next one here? The next one is S sub 4. I really want to focus on S sub 4. Oh, it's 1/3. Sorry, thank you. 1/3. Thank you. Yes. Okay, S sub 4 is 1 plus 1/2 plus 1/3 plus 1/4. Okay. Okay. And would you agree that this, okay, is greater than, this is greater than 1 plus 1/2 plus 1/4 plus 1/4. Would you agree that those two, that inequality holds? Okay, that inequality holds. That this 1/4 is less than the 1/3. Is the 1/4 less than the 1/3? Yeah. Yeah, that should make sense, right? The 1/4 is less than the 1/3. Every other term here is the same, right? It's 1 plus 1/2 plus 1/3 plus 1/4 is greater than 1 plus 1/2 plus 1/4 plus 1/4, right? Does that make sense? The 1/3 is bigger than the 1/4. Makes sense? Okay. So what I'm going to do is I'm going to focus on these things here. I'm going to rewrite this as just 1 plus 1/2. I'm going to get rid of the 3/2 there. Okay. Okay, 1 plus 1/2. Okay, and okay, and so let's look at S sub 8. Let's jump all the way to S sub 8 here. What would S sub 8 be? Well, this would be 1 plus 1/2 plus 1/3 plus 1/4 plus 1/5 plus 1/6 plus 1/7 plus 1/8, right? Okay. Okay. Okay, nice, nice, nice. Okay. Okay, and would you agree that that this thing, okay, is less than 1 plus 1/2 plus 1/2 plus 1/8 plus 1/8 plus 1/8 plus 1/8? Let's dissect this for a second. Is this true? Is this true? Well, the first two terms are the same, right? So the first two terms are the same in this, right? But then we get this 1/2 is less than these two guys, right? 1/2 is less than, where did that 1/2 come from? Well, that 1/2 came from the fact that 1/4 plus 1/4 is less than 1/3 plus 1/4. And what's 1/4 plus 1/4? Well, that's 1/2, isn't it? Isn't 1/4 plus 1/4 1/2? So isn't 1/2 less than this thing here? Does that make sense? Okay, and then what about this whole 1/8 thing? That just comes to us with the fact that 1/8 is less than 1/5, 1/6, and 1/7. So these are all bigger than 1/8. Right? But then what happens when I start adding these things together? Well, right, well, what is this equal? This is 1 plus 1/2 plus 1/2, which is 2. So this thing is bigger than 2. The S sub 4 is bigger than 2. And what is this thing going to be? Well, this was 2 plus, what's 1/8 plus 1/8 plus 1/8 plus 1/8? Well, that's 1/2, right? Isn't that 4/8? So that's 1/2. So that's 2 and 1/2. So that's 2 and 1/2. So this S sub 8 is bigger than 2 and 1/2. It seems to be, it's growing. Okay, let's do one more here. Let's do S sub 16, see what happens here. Okay. Well, I'm gonna rewrite this though. I'm gonna rewrite this as this is going to be 1 plus 2 over 2, if you're okay with that. 1 plus 2 over 2, which is 1 plus 1. What's this going to become? This is going to become, okay, 4/8 plus, okay, 4/8 plus, this was 1, okay, or 2, I'll say 2/2. This was 2/2, right? Plus 4/8 plus 1. Okay. So this in terms of 4/8, I can reduce that to 1/2. This becomes 1/2. So this is 3/2. So this is 1 plus 3/2. Okay, and there's a reason I'm writing it like this, because we're eventually going to be able to see a pattern here. S sub 16. Let's do 16 here. That's 1 plus 1/2 plus 1/3 plus 1/4 plus 1/5 plus 1/6 plus 1/7 plus 1/8 plus 1/9 plus 1/10 plus 1/11 plus 1/12 plus 1/13 plus 1/14 plus 1/15 plus 1/16. That's going to be greater than what? 1 plus 1/2 plus 1/2. Okay, it's greater than that, right? Because 1/2 is less than 1/3. Okay, this whole thing was, okay, or sorry, 1/3 plus 1/3 plus 1/4 was less than 1/2. Was greater than 1/2, sorry. This thing, okay, is going to be greater than, okay, all the 1/8 plus 1/8 plus 1/8 plus 1/8 plus 1/8. Okay, because those are all, and then we're going to use 16ths on the rest of these, the rest of the eight of these. So this is going to be less than 1/16 plus 1/16 plus 16th plus 1/16 plus 1/16. Okay, so okay, so what I could really do here up here is just go plus 1/2, right? So that's 3/2. Okay, so what's this thing going to be? Plus 1/16 plus 1/16. I need 8 of these. 1, 2, 3, 4, 5, 6, 7, 8. I got them. Okay, so what is this? This is 1 plus 1/2 plus 1/2 plus, what was 4/8? Well, what's 4/8? Isn't that 1/2? So it seems like every time I'm adding another 1/2. Plus, what's 8/16? This is 4/8 goes here. Maybe I'll put it above it. 4/8 is this guy. Okay, and then what's 8/16? 8/16, that's another 1/2. So how many 1/2s do I have? I have 1 plus 4/2. Oh, okay. So let me rewrite this. Okay, so S sub 2, let's just do the powers of 2 here. S sub 2 is equal to 1 plus 1/2. S sub 4, okay, is greater than 1 plus 1/2. S sub 4 is greater than, okay, 1 plus 2/2. S sub 8 is greater than 1 plus 3/2. S sub 16 is greater than 1 plus 4/2. Okay, and so we can say S2 to the nth, right? So 1, 2, 3, 4, right? S2 to the nth power is greater than 1 plus n over 2. Okay, and so what is this telling me? It's telling me that I'm always increasing. Okay, therefore as S sub 2 to the nth power, as n goes to infinity, S sub 2 to the nth also goes to infinity. Okay, because I just keep adding another half. For every 2 to the nth that I go out, I add another half. And then I just keep adding another half, and another half, and another half, and another half. And I keep adding the same thing over and over again. This thing eventually gets bigger and bigger and bigger. Okay, so, okay, the series, okay, of 1 over n, okay, so the series, this should be S sub n. Okay, so n equals 1 to infinity of 1 over n, which is equal to, okay, the infinite, the nth partial sums, the sequence of the nth partial sums, okay, diverges. Okay, that thing diverges. Therefore, okay, the harmonic series diverges. This is the harmonic series. The harmonic series. Harmonic. Okay, diverges. Okay, now why is this? Because it doesn't go to 0 fast enough. Okay, I keep adding more and more terms. Okay, so for the first term, I add a 1. The next term, okay, I add a 1/2. Okay, the next term, I add a 1/3. Okay, and that's bigger than every time I add, 1/3 and 1/4, I add another 1/2. Okay, and then if I add a 1/5, 1/6, 1/7, 1/8, okay, all of these, okay, so this is 1/2, this is bigger than 1/2, this is bigger than 1/2, okay, greater than 1/2, greater than 1/2. If I did my 16ths, that would be greater than 1/2. If I did 32nds, that would be greater than 1/2. If I did 64ths, that would be greater than 1/2. And so if I keep adding another something bigger than 1/2, I'm always adding extra stuff. This thing does not go to 0 fast enough. Does not go to 0 fast enough. Okay, and that's one of the interesting qualities of the harmonic series. You would think that it would converge, but it doesn't. It doesn't converge fast enough. But what about this guy? 1 over n squared. Is he going to converge? Okay, is that guy going to converge? And yes, this guy actually does converge. Okay, this thing does converge. Why? Because he goes to 0 pretty fast. He gets down a lot faster, and so the area under the curve, okay, becomes minimal. Okay, that's kind of a preview of coming attractions for tomorrow. Okay, does that guy converge? Okay, 1 over n squared. Okay, starting at 1, n equals 1 to infinity. Okay, yeah, he does converge. Okay, he does. Okay, we don't have a test yet to say that. Okay, we'll get that tomorrow. Okay, but he goes to 0 fast enough. Super fast. Okay, he goes to 0 super fast. Okay. Okay, last couple items here. Okay, theorem. Okay, if the series summation n equals 1 to infinity of a sub n is convergent, then limit as n goes to infinity of a sub n is equal to 0. Okay, so if it's convergent, then the terms themselves go to 0. You can't keep adding something big and getting a series that adds to a sum. Okay, if you keep adding bigger items, okay, you're kind of not in good place. Okay, so we want to make sure that the limit, this is okay. The converse is true. This only goes one way, by the way. This is one way only. One way only. Okay, so it's saying if convergent, then the limit as n goes to infinity of a sub n is equal to 0. Okay, what's the contrapositive of this? Contrapositive. What's the contrapositive of this statement? Okay, the contrapositive of the statement is if the limit as n goes to infinity of a sub n is not equal to 0, then what? Then what? What's the contrapositive of that statement? Then what? What kind of what's logically equivalent to the statement above it? Any ideas? Okay, if something is convergent, then the limit goes to 0. If the limit doesn't go to 0, then what? Yes, thank you, Susan. Then it's not convergent, okay? Have you ever taught geometry, Susan? Oh, yes, okay. So you know what a contrapositive is. There you go. Okay. Susan knows from being around high school geometry what a contrapositive is. Okay, so in the trenches, exactly. I taught geometry I taught college geometry and I taught high school geometry. I taught high school geometry probably 5 years in a row. So yeah, know that very well. So the contrapositive is if the limit as n goes to infinity of a, see, you guys are like, when am I ever going to use anything that I learned in high school, blah, blah. Well, here you go. Okay. It's for calculus class. Okay, so contrapositive, logical equivalent, then it is divergent. Divergent. Okay, divergent. If the limit then is not equal to 0. Okay, so this is what we call, okay, this is what we call the divergence test. The divergence test. This is not a test for convergence. The geometric series was a test for convergence. This is a divergence test. Divergence test. Okay? This is a test to see if something diverges or not. If the nth, this is also called the nth term test. The nth term test. Okay, if the nth term does not go to 0, it's not going to be convergent. That's it. Let me write that in layman's terms here. If the nth term does not approach 0, as n goes to infinity, then the series is not convergent. Okay, it is divergent. Okay, so will this prove something is convergent? No. No way in hell will this prove something is convergent. But will it prove something is divergent, that it's not in the ballpark? Yes. Okay, it will prove that something is divergent. Okay, so for example, okay, if I had n squared, right? Okay, if I have n squared, where does n squared live? Well, what's the limit as n goes to infinity of n squared? Isn't that infinity? So is that convergent or divergent? Is n squared convergent or divergent? Is n squared convergent or divergent? Okay, it's divergent. It's divergent. It does not go to 0. Okay, so this thing is divergent. Okay, will it prove convergence? No, it will not prove convergence. Why? Because, as a good example, okay, what else is divergent? Well, 1 over n is also divergent, right? So this will not prove whether or not something is convergent, but if it's true, it certainly is divergent. Okay, will not prove everything is divergent. Okay, but it will say if this is true, if it does not go to 0, there's no way that it's going to be in here in convergence. Okay. Okay, no way, Jose. Okay, what were some things that we saw were convergent? Well, what about 1 over 2 to the nth power? We saw that was convergent, right? Do those terms go to 0? Yep. Okay, every single one of the convergence, the nth term goes to 0. Nth term goes to 0. Okay, now will that tell me whether or not something is convergent? No. Will it tell me if something is divergent? Yes. Will it tell me if everything is either convergent or divergent? No. Not a test for convergence. Okay, why is it not a test for convergence? Because what's the limit as n goes to infinity of 1 over n? That's 0. Oh, okay, so 1 over n must be convergent, right? No, it's not convergent. Why? We just saw that. That's the harmonic series. It diverges. So this will only tell you if things are divergent. They will not tell you if they're convergent. Okay, just let you know. It's tricky business here. Okay, this will only tell you if something diverges. Okay, so let's do one last example here. So show n equals 1 to infinity of n squared over 5n squared plus 4 diverges. Okay, well, what can we do here? Well, let's do the nth term test. Okay, or the divergence test, the nth term test. Nth term, let's look at the nth term. The limit as n goes to infinity of n squared over 5n squared plus 4. Okay, I'm going to divide both top and bottom. Well, I get infinity over infinity here, so I could use the L'Hopital's rule if I really wanted to. I don't have to. I could do this algebraically if I really wanted to. I don't know, however you want to think about it. Again, we get infinity over infinity, so we could use L'Hopital's if we wanted to. That's fine. Maybe that's the faster way. Okay, what's the derivative of n squared? 2n. What's the derivative of, it's my eraser. That's the problem. It's making my screen all dirty. Okay, the limit as n goes to infinity. There's always a problem. Like there's always an issue. If it's not the internet, then it's the screen. If it's not the screen, it's the pen. If it's not the pen, it's the sound. If it's not the sound, it's the microphone. If it's not the microphone, it's something else. There's always something, always one thing that's off. Okay, 2n over 10n, right? So that's by L'Hopital's rule. Let's, what happens here? Well, this just becomes the limit as n goes infinity. Those n's cancel out. Okay, actually, no, they don't. This becomes, again, by L'Hopital's rule, this becomes infinity over infinity. The n's do not cancel out, don't. Okay, but again, I could take L'Hopital's rule a second time, and I would get 2 over 10. So the limit of, as n goes to infinity of this thing is just 1/5. Okay, and did the nth term go to 0? Did the limit as n goes to infinity of a sub n equals 0? No. Therefore what? Therefore I keep adding what is equivalent to 1/5 all the time, forever. If I'm adding 1/5 forever, is this thing decreasing? Is the sum decreasing? No, it's not. I mean, are the terms getting smaller and smaller? No, they're not. Therefore the sum keeps increasing, and it just keeps adding. Okay, think of it more like this. Okay, remember when we had our say our 1/2 to the nth, right? And we said, why does that converge? Why does that converge? Well, let's think about this for a second. Okay, so I'm gonna take 1/2. Okay, we're gonna start at 1, and we're gonna take 1/2, and then I'm gonna add to that 1/4. Add to that 1/4. Then I'm gonna add to that 1/8. Then I'm gonna add to that 1/16. And then I'm gonna add to that 1/32. And then I'm gonna add to that, right? And we said that eventually, okay, that's a really bad line. That eventually, when we go to infinity, we keep adding these things. It's still a bad line. I need to bring this down further. Okay, there's 1/2. Okay, there's 1. Okay, and there's my line, right? So there's my line at 1. This is 1. Oh my gosh. Could you seriously give me my line back? Don't be stealing my line. Okay, so here's 1. There's 1. Okay, and so we keep adding, and we keep adding these little pieces. Okay, and so what is the sum? What is the S sub n's approach? The S sub n's approach 1 as n approaches infinity, right? So it goes to 1. Okay, so I keep adding a smaller amount every time. I keep adding infinitesimals every time. Well, what would happen if I just added 1/5 every time? They don't go down. The things that I'm adding don't go down. What would the, this is a graph of S sub n, by the way. This is S sub n. Okay. Okay, what would the S sub n's look like? Well, if I just kept adding 1/5, then wouldn't it just be like 1/5 times n, right? Just like y equals 1/5 times n. Well, what is that? That's a straight line. That's like I'm starting somewhere, and then I just go up by, it's probably not that much. Okay, but you can see that I don't ever approach, because these terms don't go down. Okay, let's say that's a slope of 1/5. Okay, we go up 1 every 5 we go over. It's probably still too high, but I don't know. You people and your perfectionism, I don't get you. Okay, I really don't. You expect a lot out of me. all I can say. Okay, so there's a slope of 1/5. Okay, slope of 1/5. I'm going to go up, and I just keep increasing forever on this linear trajectory. So this thing is going to diverge. Okay, if you keep adding the same amount every time, it's going to diverge. Okay, it's going to diverge. You know, we're in this whole COVID thing right now, and you know they're like, you need to look at the curve, right? The curve here. Well, we did this for a long time. We started off in March. It looked like this, and then the curve went like this. Okay, this is cumulative amount. It went like that for a long time. For about 2 months, we were here. Okay, so this is like March. This is April, May. Right? April, May. Okay, and then once at middle of May hit, what happened? It went from linear growth. We kept getting about 5,000 people with new cases every day. It was a steady stream of cases. If you looked at the daily cases, it looked like this. It looked like, and then it kind of plateaued. Why did it plateau? Why is this the daily number of cases, and this is the cumulative? Right? Why is that plateauing? Because I keep adding the same amount every single time. I keep adding the same amount every single time. Then when we talk about our sums, when we just add them up, we keep adding up those partial sums, then it's a linear growth. Does that make sense? If I keep adding 5 plus 5 plus 5 plus 5 plus 5, if I keep adding 5, wouldn't 5 end up being my slope? Right? Wouldn't this be 5 times 1 plus 2 plus 3, right? Or so it'd just be n 5s. It's not that. Let me erase that. It's bad logic. Wasn't that just n, the number of days that I go along, or the number of increments that I go along? Isn't that the number of 5s? And so how would I get the sum here? Well, it's just 5 times n. And 5 is the slope of my line. So I would get linear growth. And then what happened in June? What do you think happened in June to the cumulative? In June, it went like this. Okay, boom. It hit exponential growth because everybody was like, oh, it's hot out. This thing's going to die. And that was a lie. So they're like, oh, it's probably like the flu and it's going to go away like flu season. Well, guess what? There is no COVID season. So good luck with the COVID season. Okay. And so then it's going up like this, and now it's slowly going back to linear right now, linear growth. So it then went up like this, and now we're at linear growth again. And we're still trying to push this thing down. We're still, this is California, by the way, California. Okay, so went up a little bit like that, plateaued for a little bit, and then went up. So anyway, so to go back to this thing, if it's linear growth, you're going to keep adding the same amount. That's the slope of what you're adding. You're never going to go back down. It's never going to converge to anything. I want this thing to converge. Okay, I want this thing to start converging. Okay, we want it to converge to a top level. Hasn't done it yet. Okay, so last theorem of the day. No example on this one. Last theorem of the day. Okay. Okay, if the summation of a sub n and the summation of b sub n are convergent series. Okay, if they both converge, if a sub n converges, okay, and if b sub n, I'll do the s sub n's. The s sub n's are think of s sub n as cumulative growth. Okay, S sub n is cumulative growth. Think of it again as the COVID. Some of the COVID graphs out there, they'll give you cumulative growth. They'll say, oh, we started here and we got cumulative growth, right? It just keeps going up. And you're like, well, why the heck does this graph keep going up? Because it's cumulative growth. They keep adding the number of new ones to the previous numbers. It's the total. Just think of it as in total infections. Okay, that's S sub n. What's A sub n? A sub n is your daily infections. A sub n could do whatever, right? A sub n could do whatever, but every single one of these new infections adds to your total infections. So this is daily infections. Okay, so S sub n is your cumulative. So I'm going to do an S sub n here, and I'm going to say that if this thing converges, A sub n converges, okay, if A sub n converges to some value, and B sub n converges to some value, oh my gosh, bring it back. Bring it back. There we go. Okay. So, and if B sub n converges to some value, B sub n, okay, then what can we say? Then we could say a couple of things. Any multiple of A sub n converges. So then C times A sub n converges. Okay. The sum of A sub n and B sub n must converge, equals the sum of A sub n plus the sum of B sub n, which converges. So the sum of two converging series converge, and the difference also converges. Converges as well. Okay, so the multiplication of the two, don't worry about that. That one's not good. Okay, division doesn't work either. Okay, but these are good. And we're gonna stop there for today because that was a lot of material, and I've run out of time to teach you anything else for today. Okay. Okay, so I'm gonna stop my sharing. Okay.
Professor, I have a question.
And I no longer care. Okay, I'll see you guys later. See you tomorrow. Unless you have anything else you want to discuss.
Yeah, me, Professor, I have a question.
Okay.
Yeah, so when I entered to WebAssign,
Thursday? No, I don't think homework's due until Monday. Oh.
So when I entered to WebAssign,
I shouldn't have any questions on that yet. Okay. Yeah, thank you. See you guys later. I'm gonna go heat up my lunch now.
Professor?